So, today I will be talking about one of the important property of the differentiation, that is called chain rule. You have already seen in the one variable case what chain rule tells you. If I have a composite function, say from subset of R to a subset of R, and then another function from R to R, let us say you have f and g. These are two functions from R to R. And suppose a point P is mapped to point Fp, let us say it is Q, and this Q is mapped to say R. And both f and g are differentiable. Suppose f is differentiable at P and g is differentiable at Q, then you will be having a function g composition f from R to R. So, if both f and g are differentiable, their composition will also be differentiable, and you know that the derivative of this composite function at a point P will be equal to g dash at the point Fp or Q into f dash of P. In one variable case, this is called the chain rule for derivatives. Now, we want to extend this for functions of several variables, but before doing that, first of all let us see what will happen to differential. So, whenever you have functions from R to R, it will give rise to its differential dfp. So, dfp, the differential of R, will be a linear map from R to R. This is linear, and over here you have another function g from R to R. So, this will also give you a differential of g. You can call it dg, and let me call this as df, and this is dg, this is at Q. So, once again by composing these, you will be getting dg composition df. So, whether these differentials satisfy the chain rule or not, that we are going to see. So, you can say what I will be proving, that differential of g composition f will be equal to dg composition df. This is at the point Fp and this is at the point P. This is called chain rule for differentials of the differentiable functions. Checking is easy. Let me write down the verification. Verification of chain rule. Okay. So, consider the left hand side of this rule. So, d of g composition f. Now, you remember how differential is defined. Let me recall the definition. df at a point P operating on h is given by f dash p into h. In one variable case, f dash and p and h both are real numbers, and this is the simple product of two real numbers. Okay, so, here there is no problem of matrices, etc. So, let me apply this rule over here. So, it will be g composition f dash at the point P into, if you are operating it at something h, into h. Okay, by definition of the differential of f. I am considering it at P. Okay. So, look at the right side, apply the rule of chain rule for derivatives. So, this is g dash of Fp into f dash p, and you have to multiply by h. Okay, so, I have written everything by definition. Now, look at it. So, this can be considered a real number. So, G dash is operating on Q multiplied by this. You compare it with this formula, you will say it is nothing but dg at Fp and operating on this thing. Now, this is our new H according to this rule. So, it is F dash P into H. So, I can rewrite it as dgFp, and look at what is there in the bracket. This is according to this rule once again, it is dFp operating on H, and the left hand side is d of G composition F at P operating on H. Now, this is dgFp composition dFp operating on H. So, this is true for every H, and therefore, this equality is established. So, this is the chain rule for differential of a function in the setting of real numbers. Okay. Now, there is another important thing that I need to tell you before going for the chain rule for journal setting. That is, in fact, we know differential of a function. We were dealing with functions from Rn to Rm, or subset of Rn to Rm, and the f is differentiable at a point P. What happens if f of p plus h is equal to f of p plus f dash p into h plus a continuous function eta p into h. This is now our definition for a differentiable function. F will be differentiable if this formula holds, where f dash p is a m by n matrix, h is a vector of Rn, eta p is a continuous function, it is continuous at 0 multiplied by norm of h. So, everything we will check from here. Now, this quantity is a linear function of h, and usually we denote it by dfph. And now, this is a finite number, so evaluated at h. So, this is what I have to prove. So, and this is an important observation, you may call it a lemma. It says that the norm of dfp at any h is always, or you may better call it v, it is always less or equal to m times norm of v. Okay. So, this tells you it is finite, it has this an upper bound. Okay. So, to prove this inequality, let us recall. So, recall that dfpv, if you remember last time I had obtained it. So, it was in fact summation vi, we were using a capital F at that time. Okay. If you want to use capital F for Rn setting, so okay, change it. Okay. So, everywhere this is our convention that we use capital letters for Rn setting and small letters for R. Okay. Vi, so f is a function from Rn to Rm, so this capital F will have m components, they are denoted by f1, f2, f3, etc. Vi del f2 upon del xi it goes up to Vi del Fm upon del Xi. Where?
So starting with F orange.
Yes, yes. All right, so this is the thing. You can further also write it down like this. This is nothing but the inner product of vector v and gradient of f. So we have also written it like this: v del f1 upon gradient of f, where v1, v2, v3 they are the components of v, and the second one is v gradient of f2, and so on. You go up to the mth component, that is v comma gradient of fm. Alright, so this is dfp of v. I have to compute its norm. So norm I can write down now. So norm of dfp fp of v will be equal to, now these are the components of the vector dfp. So when you will take its norm, so it will be the square of the component. So it will be equal to square of summation del fi. Okay. Okay. This plus this plus this and so on, and with every one you have to consider the vector. If you have square, so okay. All right, now this is the inner product of two vectors. Both of them are vectors. So inner product of two vectors, if you are working in the Rn setting, it will be in fact norm of v into norm of del fi I into cosine theta I, square, square, square. Okay. Now cosine square theta, for every theta would lie between 0 and 1. So in fact this would be less or equal to norm of v square into norm of summation is there. Summation you can write down outside, okay. Del fi square.
So less than 2. Not equal.
This quantity is equal to this.
So in the next last.
Okay. Yes, less or
You are taking the maximum equal.
yes, less or equal to. All right. I is running from 1 to m, that is understood. I am not mentioning it, but that is there. Now this quantity, because they are finite partial derivatives, its component are partial derivatives. So derivatives are finite. When you will take the norm, you will get some finite number. So this will be equal to, when you will take the sum, it will also be finite. So let me call that number as something m into norm of v square.
And square v square was.
You may call it m or m square. So this is some finite number. So dfp, or you, if you like, you can,
Yes.
because square you want to remove. So norm of this is less or equal to m times norm of v. So that is an important observation, that dfp is a finite quantity. It is bounded by this number. All right. So this observation will be used while establishing chain rule for functions from Rn to Rm. All right. Now we are in a position to establish the chain rule for general case. So let us consider chain rule general case. So consider functions from an open subset of Rn into some open subset of Rm, and that open subset will be land into Rk under a function g, let me call it f, and this is g. Their composition will be G composition F. You may call it H. So I have to see what about the derivative of H, whether it satisfies the similar kind of chain rule. The answer is yes. What I will be showing that d of G composition F, that is d of H, is equal to dg composition df. Okay, same thing you had for one variable case also, and this will happen at every point wherever it is differentiable, both of them. Okay, so let us start with h of something at a point p plus say x. Okay, minus h of p. Okay, h means G composition F. So I have rubbed it off, f of p plus something say h is equal to f of or minus f of p. According to the definition, it should be equal to f dash p into h plus eta p h into norm of h. Okay, this is the definition of differentiable function. Okay, so I have to see whether I get a similar kind of thing over here. What should happen? Here you must have a linear map. This should be a continuous function and eta. So I will search it out whether this happens or not. So this equal to h of, h is what? It is G composition. G composition F at the point of p plus x minus G composition F of p. Okay, or you can directly write down G of f of p plus x like this. Now what I will do, I will write down f of p plus x. F of p plus x I will write down as f of p plus something y. Okay, let me write down f of p plus x equal to f of p plus something, and that something I am calling as y.
So f is linear here?
No, it is not. No, it is not linear. अगर ये लीनियर होता तो हम लिखते इसको f of p प्लस f of x, लेकिन हमें मालूम नहीं कि क्या चीज़ आ जाए. सब्ट्रैक्शन भी हो सकता है, बट y is may be positive, may be negative, so it will be something like
Y is something.
So this is equal to y equal to f of p plus x minus f of p. And f of p plus x minus f of p, since f is assumed to be differentiable at p, will satisfy this equality. So this will be equal to f dash p into x plus some eta p of x into norm of x, where this is relation number 1. Okay. Huh? Okay.
Right hand side is positive.
Okay. F of p plus a equal to plus a. This is
minus f of p.
f of, this is minus f of y equal to f of p plus h minus f, and this quantity from here. Okay. Okay. So here eta p is continuous at 0, which means limit of eta p when x tends to 0 is equal to eta p at 0, which is 0. This should be kept in mind. Okay. So this is equal to g of f of p plus x, f of p plus x. So this I will be calling as a what? Fp plus x. Okay. So I will, let me call it fp plus y. Okay. Okay. And minus g of fp को हम क्या कह रहे थे? आप ऐसा कीजिए, इसको p कहिए, fp को आप q कह दीजिए और gq को चाहें तो आप r कह दीजिए, थोड़ी अपनी आसानी के लिए. तो ये q हो गया और fp जो है वो q हो गया. ठीक है. Again you have assumed that g is differentiable at the point q. So by definition gq plus y minus gq must be equal to what? This is my definition. So this will be equal to g dash q into y plus some eta q at y into norm of y minus.
So not minus, it is already there.
It is there. Okay, I'm sorry.
Yes.
Right. Now let me write down the values. Okay, where should I write down? I can rub off this part. So the left hand side is g composition of p at p plus x minus g composition f at p. This is the left hand side. Now, so right hand side I am writing, right hand side is equal to g dash operating on fp. Okay, दोबारा से मैं f लिख रहा हूँ और y को आपने बताया. ओके, y को आप अभी आप y ही रहने दीजिए प्लस y को चाहें तो लिख दीजिए या रहने दीजिए अभी ईटा p ऑफ y को लिख लीजिए. y क्या है वहाँ से देखिए, f ऑफ p प्लस x माइनस f ऑफ p. ओके, लेकिन हमको चाहिए होगा g डैश ऑफ एफ क्यू इंटू एफ डैश पी. तो हम ये लिख, ये क्यों? ओके, वाई शुड आई राइट डाउन? आई मस्ट सब्स्टिट्यूट फ्रॉम रिलेशन नंबर 1. सो दिस इज एफ डैश पी इंटू एक्स प्लस ईटा पी एक्स इंटू मॉडुलस ऑफ एक्स. ओके, सो दिस टर्म आई हैव रिटन प्लस ईटा पी, इसको ऐसे ही रहने दीजिए. ईटा वाई इज व्हाट? ईटा क्यू, सॉरी, ईटा क्यू वाई इंटू नॉर्म ऑफ वाई. Let us simplify a little more. So this is g dash fp into f dash p into x plus g dash fp into eta px into modulus norm of x प्लस आप क्या कीजिए, ओके नेक्स्ट लाइन में कर लेंगे, इंटू ईटा क्यू वाई इंटू नॉर्म ऑफ वाई. Now I can rub off this line as well as this one. Okay. So this term you keep as it is, g dash fp into f dash p into x plus, from this term I will take modulus of x common. So, this is g dash f p into eta p x and plus eta q y into mod of y upon mod of x. I have taken mod x common. Okay. Now, this term in the bracket I will call as some epsilon p. Now, this expression look like what I want, that this should tends to 0 when p tends to 0. This is eta p of x, in fact. It is a function of x also. Y is also a function of x. So, I will call it eta p x, epsilon p x. So, what I want to see now, whether this tends to 0 and it is a continuous function at 0 or not. We can remove this thing also. So, look here, when x tends to 0, eta px also tends to 0, because eta p we have assumed in the beginning is a continuous function. Similar thing we have for eta q also. Eta q also tends to 0 when y tends to 0. This is also known to us. I will make use of this fact. So, this term tends to 0, so means it is a continuous function. Eta q y will also tends to 0 when y tends to 0. But we have to see what about this. ये टर्म अगर 0 को टेंड करता भी है, जब y 0 को टेंड कर रहा है, तो ज़रूरी नहीं है कि ये भी 0 को टेंड करता है, क्योंकि इसमें y भी है और x भी है. अगर मैं ये दिखा दूँ कि नॉर्म ऑफ y अपॉन नॉर्म ऑफ x इज़ ए फाइनाइट नंबर, आई विल बी डन. ओके, तो इसको दिखाने में सिर्फ यही एक कसर है कि हमें किसी तरह से ये दिखाना है कि नॉर्म ऑफ y अपॉन नॉर्म ऑफ x is a finite quantity. That is what I am going to show. All right. Now, for that, what I have is norm of y I know. So, we know that. What is y? F of p plus x minus f of p, and this is equal to f dash p into x plus eta p x into modulus of x. This is y. Okay. So, we know that y equal to this, and there this implies norm of y is equal to norm of f dash p into x plus eta px into norm. And this will be less or equal to this vector, and it will be less or equal to, in fact it will become a vector. This vector, matrix multiplication vector, and this is a vector multiplied by scalar is a vector. So, it is a sum of two vectors inside the norm. So, it will be less or equal to f dash p into norm of x plus eta p x into norm of x. Now, I can take norm common from here. So, it will become f dash p plus norm of eta px into norm of x. And this implies that norm of y upon norm of x is less or equal to norm of f dash p plus norm of eta p. Now this quantity TFP का norm आपने देखा था finite है, and therefore the norm of this is all finite. This is already tends towards 0, so the right hand side is a finite number. So this proves that this quantity is a finite number. Finite number. And therefore this quantity tends to 0 multiplied by a finite number will tends towards 0. That shows that epsilon p is a continuous function at 0. This implies epsilon px tends to 0 when x tends to 0. Okay. Now look the entire picture in the light of this formula. So what we have got? Should I rub it off? Now the whole thing is, left hand side is G composition F P plus H minus G composition F at P equal to. The first thing is, what is this? This is G dash of Fp into F dash P multiplied by x, okay, plus a continuous function epsilon px into modulus of x. This is a linear term of x, this is a linear term of x, this is a continuous function of x, and therefore G composition F is differentiable at the point P. And what is the derivative? This is the derivative. So from here what do you notice is that the derivative of G composition F is equal to G dash of Fp into F dash of P. And therefore chain rule is satisfied. This is what the chain rule is. Is it right? And you are done. This completes the proof. The only difficulty that I see over here that I don't have space to write the language. So I have already explained the points, the language one can check from the notes. So I stop at this point. The other things are quite lengthy in nature, so I have to stop at this point. Okay.